are going to discuss about BH characteristic of any magnetic material which are being used in transformer. Now B stands for magnetic flux density and H stands for magnetic flux intensity. Now B is just a ratio between flux to area, and H is a ratio of number of turns in multiplication with current divided by magnetic path length. This is MPL, magnetic path length. Now in order to estimate this magnetic path length L, say for example if we are using this core for the transformer, now this is having height of L1 and width of L2. So its total length would be 2 times of L1 plus 2 times of L2. So considering that, and if you are taking n number of turns here and current flow through this primary is I, so flux strength can be given as multiplication which will be divided by magnetic path length, and flux strength, flux density will be the ratio of flux upon unit area. So the area is, let's say this core is having this particular width, so this will be the area, like area enclosed by this, so that would be the area, flux upon unit area. Now BH characteristic, so it can be seen like on x-axis and y-axis. So hysteresis comes from Greek word hysteren, whose meaning is lagging. Now when AC current flows through any magnetic material, then magnetic core material undergoes the cycle of magnetization and demagnetization. Magnetization is the process by which some magnetic flux will start setting up in the core, and demagnetization is again the reverse process where magnetic flux will start to reduce. Now here the property of magnetic material is that while you energize the magnetic material, so at that time magnetic flux will be lagging behind the magnetic field strength. So in short, the flux phi will be lagging behind the H. Okay, this is known as a hysteresis. Now this is the BH characteristic of any magnetic material. So this will be in the normal mode. Say for example, if we have one magnetic material and some turns is on there, so if you start applying current in forward direction, so here current is 0. Okay, as we discussed, this is ratio of Ni upon L. Now here we will be having 0 ampere. Now at that time there will be some flux, residual flux will be there. Now if you start applying more and more current, so this reverse flux will start approaching to 0 point. So with some minimum current will be required in order to have a 0 flux in the core. Now again if you continue to apply the current in the same direction, okay, here at this point I will be 0. Now here again if you plot, let's say I1 current is flowing at this point, and at this point let's say I2 current is flowing. Now if you go beyond this current, then more there will no more magnetic flux. This is something known as the saturation of any magnetic material. Now if we compare I1 and I2, then I2 would be greater than I1, because I2 will be corresponding to this value and I1 is corresponding to this value. Okay, so this is I1 proportional to I1 and this will be proportional to I2. So I2 will be greater than I1. Now if you start applying current in reverse direction from this point, while you reduce the current again, so this magnetic material will follow this path, and at this particular point your current will be 0 again. Now if you continue to apply the current in the reverse direction, example over here, so your current will become reverse now. This is I1. So it will